All right, good morning, everyone. Let's get started. So, before we start with the class, a couple of announcements. So, you would have noticed that the next homework is already up on Piazza. So, you can find the actual homework on Google Classroom, but no, a post has been made on Piazza as well. Also, the tentative list of topics or suggested list of topics have been put up, and the link for that has also been put up on Piazza. You are free to choose any topic from this list, but at the same time, you can also explore other topics which you might be interested in. If you're interested in any topic which is not in the list, then please send me an email regarding what topic you're specifically interested in. Uh, Right, so that's about it. So we'll have the next class. So we couldn't, unfortunately, I couldn't take class on Monday. So we'll have a makeup class at 4 p.m. today. All right. So let's get started. In the previous class, we were talking about multiple access channels, where you have multiple senders and one receiver. And the goal now is to communicate reliably in this channel. So each sender has its own message to send to the receiver. So obviously there is crosstalk, and the goal of the receiver is to recover each of the individual messages, right? And our discussion was focused on the two user discrete memoryless multiple access channel, where you have two senders, one receiver, and the channel is memoryless given by the following joint distribution. So we assume that the input and the output alphabets are finite, and we'll see that a lot of this is fairly general. It also extends to continuous alphabet channels through the sort of discretization trick. You just even though it's a continuous alphabet, you convert it to a discrete alphabet, and then as you make the number, as you kind of make the resolution of the alphabet smaller and smaller, as you make it finer and finer, the rates that you can achieve for the discrete alphabet, the quantized alphabet channel, or the discretized alphabet channel, turns out to converge to that of the continuous alphabet channel. Right. So that is why it suffices to look at discrete channels, and that is why our focus will be on discrete alphabet channels. But later on, like after we study this in detail, I also discuss Gaussian two-user multiple access channels. All right. So here we have two users who have messages of length kn and ln respectively, and they can use n channel uses to simultaneously communicate with a receiver. So the encoder is going to be a function so the encoder for user 1 is going to be a function which take these kn message bits and gives an n length code word. And the encoder 2 is going to be a function that takes ln message bits and outputs a code word x2n, and these are simultaneously transmitted across the channel. The receiver gets yn, and then given yn, the decoder estimates the two messages m1kn and m2ln. Right, and so the rates are going to be r1 and r2. So kn will be n times r1, and ln is going to be n times r2. And the goal is to ensure that these encoders and decoders satisfy the following property: the probability of error, or the probability of block error, is vanishingly small. So the probability that either of the messages are decoded incorrectly tends to 0 as n tends to infinity. And if this happens for some r1 comma r2, then we say that r1 and r1 comma r2 is an achievable rate pair. And our interest is in finding out the set of all achievable rate pairs, which we call the achievable rate region. And we had some discussion, some simple inner and outer bounds, and the outer bound looked like a pentagon, whereas the simple inner bound looked like a triangle. And I also discussed that The actual achievable rate region lies somewhere in between these inner and outer bounds. Right? In particular, so given any pair of PMFs Px1 and Px2, the following set of rate pairs is achievable. So the pentagonal region consisting of R1 less than or equal to the mutual information between x1 and y given x2, R2 being less than or equal to the mutual information between x2 and y given x1, and the sum rate being less than or equal to the mutual information between x1, x2, and y. This forms a pentagonal region, each of these. So the first condition corresponds to a vertical line in the R1, R2 space. The second condition corresponds to a vertical line, or basically a half space in the R1, R2 space, and the sum rate R1 plus R2 equal to something gives a sort of a diagonal line, right? It's a line with slope -1, right? And the intersection of these three regions gives some pentagon, and this is achievable for every Px1 and Px2. So corresponding to each Px1 and Px2, we get a pentagon, and the capacity region is the closure of the union of all of these pentagons. Right. So for each of these pentagons, we get each Px1, Px2, we get one particular pentagon. Take the union of all of these and take the smallest closed set or the smallest convex set containing all of these, and this gives us the achievable rate region. All right. So our goal was to show at the end of at least as a first point, our goal is to show that for any Px1, Px2, the pentagon is achievable, and the way we show this is by looking at just the corner points. To show that any rate pair in the pentagon is achievable, it is enough to just show that these two corner points are achievable, because after all, we can use time sharing to show that the line joining or any point on the line joining these 2 points is also achievable, and consequently any point in this pentagonal region is also achievable, right? And the way we show that, and the way we are going to show that these corner points are achievable, is using what is called successive cancellation decoding. All right. So any questions until this point? Okay, so let's go ahead and do that. We'll show that every point in the rate. Yeah, so we'll show that one of the corner points is achievable. In fact, we'll look at the following corner point. So you fix a Px1 and a Px2. Our goal is to show that the following rate pair is achievable. So R1 equal to the mutual information between x1 and y. Minus epsilon for some small epsilon greater than 0. R2 is equal to the mutual information between x2 and y given x1, so that corresponds to would correspond to the following rate point. Right. And the way we are going to show that this is achievable is by looking at random codebooks. So for each user, you independently generate a codebook. So by that, I mean that every code word, so after all, to describe a codebook, you need 2 to the NR1 code words for user 1 and 2 to the NR2 code words for user 2. And each code word is randomly chosen. So you pick a random codebook by independently generating a code word. So you generate 2 to the NR1 code words for user 1, 2 to the NR2 code words for user 2, and then share these code books with the 2 users. The decoder, of course, knows both code books, right? So everyone knows all the code books, and then as and when you get a message, you encode and then transmit. And we will analyze these random code books. So how are the random code words generated? So each entry of each code word is generated IID according to px1 for user 1 and px2 for user 2. Right, according to px1 for user 1, px1 for user 1, and according to px2 for user 2. Right, so basically there are 2 to the nr1 code words, each of length n, and for user 2 there are 2 to the nr2 code words, each of length n. The encoding process is simple. Suppose you want to transmit, the user observes the message. So the user gets a message which is uniformly distributed so it's a sequence of nr1 uniformly random bits. So it gets one of these messages 00000 up to 11111. All right. So for suppose that the ith message is seen by user 1, so it just transmits the corresponding code words. So after all, the code book is just a table of code words. So it transmits the corresponding row of this code book table, right? And user 2 does the same thing. All right. So that is how the encoding process works. The decoding process is a little more complicated. The decoder first decodes one of the two code words. So essentially, it decodes the code word corresponding to user 1 first, assuming that the code word transmitted by user 2 is part of the noise. Right? So you first decode code word 1, and then having decoded code word 1, or having decoded the first message, you use this information in order to decode the second code word. So you assume that, so first you make an estimate of the first code word, and then treat as though this was the actual transmitted code word, and use this to decode the second code word. So for example, if it had been an additive channel, then one way to interpret this is that you decode code word 1 and then subtract code word 1 from the received signal, and then from the subtracted signal you decode code word 2. All right. An equivalent way, or a more general way of describing this approach is the following. So the way you decode code word 1 is in the following manner. You find, so the estimate of code word 1, x1n hat, is basically that unique code. If there is a unique code word in codebook 1, which is jointly typical with respect to the received signal, then you declare that as as your estimate. If there is no code word which is typical with respect to yn, or if there is more than one code word which is typical with respect to yn, then you treat it as an error. You just declare the first code word as your estimate. Okay.
Hello.
Yes.
Yeah, sir. So whoever we decoded first, then possibility of getting more error in first case is more, or in second case is less, because we have some shared information. These kind of things.
Correct. So let's see what happens. So let's go back to the rate pair. Okay. So in some sense, who do you think will see a better channel, user 1 or user 2? So remember, sorry.
So user 2 will be
Correct. So user 2 in some sense gets a better channel, right?
yes.
Because when you're decoding the signal corresponding to user 2, you have already removed the component corresponding to user 1. And that is in fact reflected in the rate region. So remember that we're looking at this point in the pentagon, right? This particular point. So indeed so user 2 will be transmitting at a higher rate than user 1. So user 1 is only transmitting at I of x1 y, which is strictly less than, or at least for most channels, this will be strictly less than ix1 y given x2, whereas user 2 potentially sees a much better channel. Of course, this is assuming that the channel is somewhat symmetric, but in general it could be different. But generally speaking, user 2 sees a better channel and therefore can operate at a higher rate than user 1.
Okay.
All right. Yeah, okay,
Yes.
that's a good question. Any other questions? Okay. Okay, so that's how decoder 1 decodes it's the decoder and the decodes the first code word. Now, having decoded the first code word, the second code word is decoded as follows. So you find if there is a unique code word in the second code book, so if there's an x2n in the second code book, such that x1n hat, which was decoded in the first stage, x2n and yn are jointly typical, then you declare that as the corresponding code word. If there is more than one code word, if there is more than one x2n, which is jointly typical with respect to x1 hat and yn, or if there is no code word which is jointly typical with respect to x1n hat and yn, then you declare an error, or you treat this as an error, but the decoder can just output some random code word, maybe the first code word. All right. So that is how the successive cancellation decoder works in general. Now, specifically for additive channels, so for example, for the BSC or for the AWGN channel or for any additive channel or for suitable additive channels, you can show that this is identical to first doing, or instead of this, what you could also do is you first do minimum distance decoding at the first stage, right? Find the closest code word in the first code book with the received signal. And then in the second stage, you remove you subtract out the decoded code word in the first stage, and then do minimum distance decoding to decode the second code word. And you can show that this kind of decoding also achieves the same rate pair. And in fact, for such channels, for such additive channels, the minimum distance decoding approach will give you a lower probability of error than what you get using the successive cancellation decoder. But that is specialized only to certain channels. So in fact it's easier to look at the successive cancellation decoder in this general setup using typical sets. Right? But any sort of decoder where you decode the code word sequentially can be called as, in some sense, a successive cancellation decoder. All right, so let's show that if using the rates defined over here, if we transmit at these rates, and if we use the successive cancellation decoder at the receiver, then the probability of error is vanishing in n. And essentially all that we need is the packing lemma that we studied in one of the earlier classes. So let's just recall what it is. I won't prove it once again because we've already done it. So the packing lemma says the following. Suppose that we have two sequences, yn and un, which are distributed IID according to some joint distribution PYU. So u and y are correlated, but then across time, across the i's, the components are all independent and identically distributed. Okay. Now, if we generate m code words, so to speak, or m sequences, IID according to px given u, then as long as this number 2 to the nr is small enough, as long as it is less than the mutual information between x and y given u, the probability that these xn of m's, xn of i's are jointly typical with respect to both un and yn, this is vanishing in n. Okay, so in some sense, so you have yn and un, and then you're independently picking points according to px given u. So if as long as there are not too many such points, as long as you're not picking too many points, the probability that any one of them is jointly typical with respect to yn and un, this is small. But on the other hand, if you pick too many points, then obviously you'll find at least one point which is jointly typical with respect to yn and un. So all this is saying is that as long as r is less than this specific quantity, the probability that these three are jointly typical for any m is vanishing in n. All right, and we'll apply the packing lemma for different sets of yn, un, and xn. All right, so let's look at the successive cancellation decoder. Now, can someone tell me what are the error events that might happen? So can someone tell me one error event? And can you tell me one event which can lead to an error?
The decoded one tending which can be equal to some other code word, not the actual one.
Okay, fine. So that's so which one? There are two stages, right? And in each stage, you can get an error.
So in the first stage, the x1, there is the first signal which we are decoding.
Correct. So the first thing is where you're saying is there is some x1n of I, where I is not equal to 1, and x1n of I and yn are jointly typical. All right. So that is one error event.
In the second stage for the user 2, even if x1 fails, then x2 also fails.
Yeah. So that is already covered by this event, right?
Okay. Yes, sir.
Or fine. So there are different ways to do it, but sure. So in fact there are three things which can happen. So either x1 is not jointly typical with respect to yn, x2 is so there is some other code word in the second code book which is not jointly typical with respect to the code word. So let's see, x1n. So okay, so first let us assume that code word 1 was transmitted, right? That can be done without loss of generality. Since all the code words are generated IID, so let's assume that the actual message to be transmitted is the all zeros message. Okay, or the first message is actually transmitted. Okay, so three things can happen. Either
the first doesn't belong to typical set at all.
Which one?
Any okay, first user 1, it won't belong to typical set.
Yeah. So note that this is the message, right? So corresponding to this message, there's a code word which is generated IID.
Yes, sir.
All right. So that code word. So one potential thing, of course, is that these code words are not typical, right? Code words corresponding to the first message and code words corresponding to message of user 2. So x1 n of 1, x2 n of 1, and yn, these are not jointly typical, right? So the true code words are actually not detected correctly. So it's possible that the first code word, or the actual code word corresponding to user one, the code word corresponding to user two are not jointly typical with respect to the received sequence. The second case is where there is some other code word which is also jointly typical with respect to the received sequence. Right? And since there are two stages, it can happen in two different stages. So there is one which is jointly typical with respect to epsilon. So it's possible that for some I not equal to 1, there's a code word in the first code book which is jointly typical with respect to yn, or we could also have the case where the code word corresponding to the second user, there's some other code word in the second code book which is jointly typical with respect to the received sequence and the actual first sequence. Or there could be two code words which are completely different. I not equal to 1, j not equal to 1, and x1 n of j, x2 n of I, and yn are in the typical set, right? So the four conditions are the following. The first condition is that the actual transmitted code words are not jointly typical with respect to yn. The second case is that, let me put this a little differently. The second case is when the first code word, there is some other code word in the first code book. There is some other code word in the first code book which is jointly typical with respect to x2n and yn, the actual code word corresponding to user 2 and yn. So this is the actual code word. This is some other erroneous code word. Similarly, there could be the case when the actual code word from codebook 1 and an erroneous code word from codebook 2 are jointly typical with respect to yn. And this is the case when an erroneous code word from codebook 1 and an erroneous code word from codebook 2 are jointly typical with respect to yn. All right. So these are all the possible error events that could happen, right? Because here the cases are, so you make an error when either the true code word is not jointly typical, or there is some other code word which is jointly typical, right? And this takes care of all the possibilities, right? So the true code words are not jointly typical. There is an erroneous code word from codebook 1. There is an erroneous code word from codebook 2. There are erroneous code words from both codebooks. If none of these happens, then decoding is successful. Right? Any questions? So there are some confusing code words or some erroneous code words coming from some of the other code books, right? Uh, so one way of sort of geometrically thinking about it is the following, and again, this is purely for intuition, but essentially this is what happens in general. So let us suppose that the first user transmits one particular code word, right? Uh, so let's assume that it's some sort of a like a Gaussian channel. So let's assume that that user one transmits one particular right. So user one transmits a particular x1n. This is the true code word, and the second user transmits a code word x2n. Right, and let's assume that, okay, so maybe one thing is, let me draw it a little differently. Right. So let's assume that this is the origin. Right. So this is the origin. And let us assume that user one has to satisfy some power constraint of np1 or p1, and user two has to satisfy a power constraint of p2. All right. So effectively, the x1n norm x1n should be less than or equal to square root np1. Norm of the second code word should be less than or equal to square root np2. Now let's suppose that we choose Gaussian distributions to generate these two code books. Now if we choose Gaussian distributions, then with very high probability, these conditions will be satisfied. So both x1n and x2n will lie within a ball. In fact, they lie in a thin shell of radius square root np1 and square root of np2 respectively. So let's assume that this was the actual transmitted code word x1n. Okay, the first code word. Now user 2 transmits another code word. Again, maybe this was so user 2 maybe has some other power constraint. Let's call it np2. So user 2 transmits this particular code word, let's say. x2n. All right. So the received sequence is maybe x1n plus x2n plus some noise. Right. So this is x1n. This is x2n. So geometrically, the sum is going to be something like this. Right. This is going to be x1n plus x2n, and there's maybe some additive noise, which is also Gaussian of some certain variance. So let's say that this, let's say that the received sequence lies somewhere over here. All right, this is the yn. Okay, so this is what the geometry will look like. if you use Gaussian codebooks and you transmit it through a Gaussian MAC, right? So now, given this, you have to decode. So what does the decoder do? So first you treat x1n as part of the noise, right? So you want to know if, sorry, you first decode the first user, right? The code word corresponding to the first user. So what will the typical set for xn and yn look like? So for part one of decoding, so x1 n comma yn belongs to the typical set. One way of looking at it for these AWGN type channels, or at least the intuition, is that the norm of x1 n should be close to square root np1. The norm of yn should be close to square root n times p1 plus p2 plus sigma square, and square root x1n minus yn. So the distance between x1n and yn should be close to square root n times p2 plus sigma square, right? Because when you're decoding x1n from yn, the total noise component is sum of the AWGN and the second code word x2n, right? And x2n can be thought of as Gaussian with mean 0 and variance n times p2, and the AWGN has a variance of sigma square, right? So the first stage of the decoder is to make sure that there is exactly one code word. So you look at yn. So the decoder looks at a ball of radius square root n times p2 plus sigma square. If there is a unique x1n in this particular region, then it declares that as the corresponding code word. So given yn, you look within a radius of square root n times p2 plus sigma square. If there is a unique code word in the first code book, then you declare that. You declare this as the actual transmitted code word. If there is more than one code word, so maybe if there were one other code word in the code book, maybe over here, then that would correspond to an error. Or if x1n were not within this particular distance of yn, then that would also correspond to an error. So those would be the two sort of errors for the first stage of decoding. Right. So having decoded this, you look at whether x1n, x2n, and yn are also jointly typical. So in addition to these, the second condition, you also want to check if norm x2n is close to square root np2, and if norm x2n minus yn minus x1n, so having removed the component of x1n from yn, does x2n lie within distance n sigma square, square root n sigma square from x to n, right? So having removed this, so from yn, you look at a distance of square root n sigma square. So yn minus x1n would be something over here, maybe. And the typical set decoder checks whether x2n lies within distance of square root n sigma square from the subtracted sequence, from this part. Right? If there's more than one code word in the code book lying in this particular region, then you declare that to be an error, or if there is no code word, you declare that to be an error. Right? So that's sort of geometric. That's a geometric interpretation of how the typical set decoder works. Now to verify this, you should actually try it out. For example, you can take the BSC. That's a good example to always work with. Take the BSC and then compute all the typical sets. So compute, so find out what each of these events correspond to, and try to represent these events in terms of the Hamming distance. Right. So in fact, in the second assignment, you'll be doing something similar, but for the point-to-point BSC. Right, but you can do this for a slightly more complicated binary symmetric MAC, where yn is equal to x1n XOR x2n XOR zn, where zn is maybe some Bernoulli p, and x1n and x2n should have maybe a Hamming weight of less than or equal to n times q. Right? So you can think of complicated channels, and each of these channels can have, all of these channels have a similar geometric interpretation, right? So the typical sets correspond to essentially balls, and whether a sequence is typical or not depends on whether the corresponding sequence lies within a certain distance from a certain point or not. All right. So this intuition takes some time to get, but once you get it, it feels very natural. All right. So we have each of these error events, and we want to analyze the probability of error for each of these events. Right. So we know that at least for the first event, the probability of error is vanishing. So the probability that, since all of these are IID, so event E1, the first error event, so the probability that x1n n of 1, x2n of 1, and yn, the actual sequences, are not jointly typical. So we know that these are distributed IID, each component is distributed IID according to px1, x2, y, which is px1 of x1, px2 of x2 times py given x1, x2. This is specified by the channel of y given x1, x2. All right, and just by properties of the typical sets, we know that the probability of that the first error event occurs, this is vanishing in n. So it's 2 to the minus epsilon square times some constant times n. Right, so let's look at the second event, E2, and that is, let's look at the event that x1 n of I, where I is different from 1, x2 n of 1, and yn, these are in the typical set. And this happens for some I not equal to 1. Right? So I can be in 2, 3, up to 2 to the nr1. Right? So in this case, you know that yn and x2n of 1 are correlated with respect to each other, because this is the true code word sent by user 2. Whereas these code words, so the first user transmits the first code word, right? And all of these other code words for I equal to 2, 3, up to 2 to the nr1, they're all independent of the first code word, and hence independent of x2n of 1 as well as yn. Right? So these are IID distributed according to px1 of x1, px2 of x2, and yn, sorry, py, and yn depends only on x2. Right? So unlike the first case where y depended on both this x1n and x2n, if for computing the probability of this event, x1n of I is independent of yn and x2n of I, because these are erroneous code words and these are not transmitted. Right? These are some other code words which are independently generated. So for this, to find the probability of error, E2, this is less than or equal to 2 to the minus n delta 1 of epsilon by the packing lemma, right? So we'll use the following packing lemma where yn and un are correlated with respect to each other. So here the packing lemma of yn is the same as in so the yn over here is the same as the packing lemma's yn, but un will be x2n of 1. Right? So as long as the rate r1 is less than the mutual information between x1n, or the mutual information between x1 and y given x2 minus epsilon, this probability of error is vanishing in it. Similarly, for the third error event, we want to know what is the probability that the true code word for user 1 and an erroneous code word for user 2 are jointly typical with respect to the received sequence I in 2, 3 up to 2 to the nr2, right? And in this case, this code word is independent of x1n and yn, but x1 and yn are correlated with respect to each other, right? Because this is an erroneous code word, but this is the true code word. This is a true code word, and therefore it is correlated with respect to the received sequence, the actual transmitted code word. px1, px2, and now y depends only on x1. So the probability of error of the third error event is less than or equal to the minus n some delta 2 of epsilon, again by the packing lemma. But now we take, in the packing lemma, you take un to be x2n, and xn is taken to be x1n of I. Right, so the probability of error is vanishing as long as there are not too many code words in the second code book. So R2 should be less than the mutual information between x2 y given x1. Right, and this is anyway satisfied. The final case is when x1n of I, there are some erroneous code words from either code book are jointly typical with respect to the received sequence. Two to the nr1 and j 2 to the nr2. Right, so again this probability as well is vanishing. Epsilon, again by the packing lemma, where you take un to be just empty and xn. So now remember that both x1n and x2n are independent of yn, because these are erroneous code words. These are not the actual transmitted code words. x1 n of I, x2 n of j, and this probability of error is vanishing as long as r1 plus r2 is less than the mutual information between x1, x2, and y. All right. So really, essentially, all of this is how you identify the correct random variables in the packing lemma. So the crucial point is to identify which random. So you have 4 error events, and once you identify what are the error events of interest, the goal is to find out what is the joint distribution of the random variables in the error events. Right. So here we have 4 error events. In the first error event, all of these are correlated with respect to each other and distributed according to px1, x2, y. In the second error event, we're looking at one true code word, one erroneous code word, and one received sequence. So we know that the true code word and the received sequence are correlated, but an erroneous code word is not correlated with respect to the true code word or the received sequence. So x1 is independent of x2 and y. And you use the packing lemma corresponding to that. So here in the packing lemma, x is independent of y and u, but y and u are correlated with respect to each other. Right? And similarly, in the third error event, x1 and y are correlated because x1 is assumed to be the true code word, but x2 is some other erroneous code word and is independent of the true code word and the received sequence. So you use the packing lemma by identifying that particular x. So in this case, X is the X2n, and X1 and Y are correlated, so that corresponds to this particular pair. And for the fourth error event, we're looking at the case when both, you could get erroneous code words from both code books, right? So some x1 of j and x2 of I are typical with respect to the received sequence. But here, if you look at the joint distribution of this triple, you know that x1 is independent of yn because it's not the actual transmitted code word. X2 is independent of y because it's not the actual transmitted code word, and x1 and x2 are also independent because the code books have been generated independently. Right. So essentially, whenever you look at any of these achievability proofs, the key step or the two key steps are: number one, you identify the right error events, and number two, once you've identified all the error events, you find out what is the joint distribution of the variables in the error events. And once you do that, it's just a matter of plugging in the right lemma. So either a packing lemma for channel coding problems or some sort of a covering lemma for source coding problems. Right? And then the rest of the proof is pretty natural, and it will at most involve some union bound or something like that, right? So the probability that an error occurs is the probability that any one of these events occurs, which by the union bound is simply less than or equal to the sum of the probabilities of these four events, and that is overall vanishing in. All right. So the best way to understand this in detail is to sort of work it out on your own. Try to think about what the joint distributions are. Try to apply the packing lemma in as many situations as possible. So try to just choose a couple of channels. So try to pick something like, so for example, we saw a couple of channels. So one is, right, so the binary erasure MAC, right? So this was one case. So try to see what the typical sets are for the binary erasure MAC. Try to see what the typical sets are for this sort of a binary symmetric MAC that I had described. So yn equal to x1n plus x2n plus zn, where zn is maybe Bernoulli P. x1n and x2n are chosen to be Bernoulli, the code books are chosen to be some Bernoulli Q. Right. So for each of these, try to simplify the typical sets, try to evaluate them, try to see what the error events will correspond to. Right, and that's the best way to gain more intuition and more understanding as to what is actually happening in these achievability theorems. Right. All right. So any questions? So it's important to note that just by reading the notes or the textbook, that is not enough, because then you don't really gain any understanding. The only way that you get comfortable with all of these packing lemmas and covering lemmas, all of these various results, is by applying them. And the best way to do it is to solve problems. So try to cook up your own problems, try to design some simple channels and try to find out, like prove the achievability result in your own way. And also look at some of the problems in both the network information theory textbook and also the Cover and Thomas textbook. So there are specific topics on the multiple access channel and just point-to-point channels in the Cover and Thomas textbook itself. So try to work out some of those examples, try to work out some of the exercises, and then once you get the intuition, everything else becomes fairly straightforward. It's only until you get that level of intuition that that it seems hard, right? Because once you get that intuition, you'll be able to think geometrically, as I described in this class. All right. So really, you should be. I mean, so there are all of these error events and then these calculations which seem very abstract, but as I keep repeating, there is a lot of this geometric intuition to everything behind this, and the only way you get intuition is to sort of do the abstract calculations multiple times till you gain a deeper understanding of it. All right. Okay, so let's stop at this point. If there are no further questions, then we meet again later today. So we'll have the next class at 4 p.m. today.
Thank you, sir.
Okay, thank you.
Good day, sir.
Have a good day.